Welcome students. Myself Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. In my lecture series of MSc Previous Physics, I am dealing with first paper, that is Classical Mechanics. We were studying Canonical Transformation. Canonical transformation means that we have to transform from old set of coordinates to a new set of coordinates. Old set of coordinates are denoted by small qj, small pj, and new set of coordinates are denoted by capital Qj and capital Pj. To check whether the given transformation is canonical or not, we have studied exact differential condition. Now, today we will discuss bilinear invariant condition to prove that the given transformation is canonical. What does bilinear invariant condition states? It states that the form summation small pj dqj minus delta qj dpj, this must remain invariant. What does here invariant means? That this factor which we have defined in old set of coordinate, this factor must remain in the same form when it is defined in new set of coordinates. That means for proof of canonical transformation, we have to show that del pj dqj minus del qj dpj, this is equal to similar factor when expressed in new set of coordinate. So, I am going to prove this condition. We have already discussed Hamilton canonical equation of motion. There are 2n number of canonical equation of motion. They are of first order and these equations state that Qj naught equal to dH upon del Pj. So, what does Qj naught means? It means dQj upon dt. Hence, it can be expressed as dQj equal to del H upon del Pj dt. The second transformation equation is Pj naught equal to minus del H upon del Qj. So, we have dPj to be minus del H upon del Qj dt. We know that Hamiltonian canonical equation of motion, they remain invariant under canonical transformation. This means the form of expression in old and new set will remain same. So, we can express these expression in our new set of coordinate as here just a simple change is that small qj is expressed as capital Qj and similarly small pj is expressed as capital Pj. Now, these first and second equation, they are satisfied simultaneously and we have arbitrary del Qj and del Pj. So, multiplying first expression by del Pj, we can have del Pj dQj minus del H upon del Pj dt. Similarly, from the second expression, multiplying it by del Qj, I have minus del Qj dPj plus del H upon del Qj dt. Now, I am taking first term and third term in a single bracket and remaining two terms, that means this second term and fourth term, they are taken in another bracket. Now we can see that this expression here in the first term I have derivative of h with respect to pj, and this is multiplied by del pj. Similarly, the second term is variation of h with qj and it is multiplied by del qj. So this terms is the variation of Hamiltonian, that means del h. Here we have taken that our generating function, it does not contain time, and we have already shown in our previous lectures that when there is no dependence on time, then old and new Hamiltonian are same. So we can express our third expression in terms of new coordinates as, where we have simply replaced capital small coordinates by capital coordinates. That means small pj is capital Pj here and small qj is capital Qj. But h remains same because f does not depend on time. So we have third and fourth expression. On comparing these two expressions, we can see that these terms, which are del Pj dQj minus del Qj dPj, this is similar to the term del capital Pj dQj minus del Qj dPj. This is the bilinear invariant form. So in order to show that whether the transformation is canonical or not, we have to prove this by bilinear invariant condition. Now to make it more clear, I am discussing one problem. I have to show that the transformation given by capital P, capital Q is equal to 1 upon P and capital P equal to QP square, this is canonical. Now here I am giving you the problem in capital QP coordinates. So I have to solve this term and we have to show it in old coordinate form. I am finding the derivatives. dq will be minus 1 upon p square dp, and similarly del q will be minus 1 upon p square del p. Now from the capital P expression, dp will be 2qp dp plus p square dq. Similarly, I have obtained the expression of del p. Now obtaining these values, I am putting them in the bilinear invariant condition. Bilinear invariant condition, on solving this condition, I get the value del p dq minus del q dp. So this shows that the given transformation is canonical transformation. So students, we have discussed two methods to show that the given transformation is canonical or not. First method is exact differential condition, and the second method which we have discussed today is the bilinear invariant condition. Now I am going to discuss infinitesimal contact transformation. In contact or canonical transformation, we have taken a change from old set of coordinates to new set of coordinates. That means we are going from small qp coordinate to capital QP coordinate. But here there will be a transformation in which old and new set of coordinates, they differ slightly. Infinitesimal means small change. That means there will be a very slight change in old and new set of coordinates. If I am taking my generating function to be summation over j, small qj, capital Pj, and since it is the second form of generating function, I am taking the transformation equations of this second form, which are small pj equal to del f2 upon del qj. So differentiating f2 with respect to small qj, I will get it to be capital Pj. That means new momenta and old momenta, they are exactly same. Now obtaining another transformation equation, which is capital Qj equal to del F2 upon del capital Pj. I get small qj. That means old and new coordinate, they are exactly same. So if I use this form of generating function, then it will generate identity transformation. But here in Feitzmel contact transformation, I am in need that my old and new coordinates, they differ slightly. In order to do this, I am modifying my generating function. Let my new generating function f be summation small qj capital Pj plus epsilon capital G, which is a function of small q and small p, small q and capital P. Here epsilon is a function, it is an independent parameter, and G is an arbitrary function. This is the second form of generating function. Since it depends on small q and capital P, again I am solving the transformation equations of second form. The transformation equation is capital Qj equal to del F2 upon del capital Pj. Differentiating my expression, I get small qj epsilon del G upon del capital Pj. Similarly, the second expression, here we can see that there is a change in coordinates. They are not exactly same. Earlier capital Qj was exactly equal to small qj. Now by choosing a new generating function, a change of the factor epsilon del G upon del Pj is introduced. Similarly, here in momenta, a change which is equal to epsilon del G upon del Qj is introduced. Now, since we know that capital Pj and small pj, between these coordinates there is a small change. So, what we are doing? We are replacing capital Pj by small pj. Since function g depends on small qj, capital Pj, we are replacing this capital Pj to small pj. So, I can get the change in coordinates as del qj will be equal to epsilon del G upon small pj, since we have replaced capital by small, and similarly here I get del small pj equal to minus epsilon del G upon del qj, G being function of small qj and small pj. Now since we have changed our generating function from f to g, now g will be termed as the generating function of Feitzmel contact transformation, whereas f is the function, generating function of contact transformation. Now I am putting epsilon to be dt and let g to be equal to h. So from the first equation, which was del Qj equal to epsilon del G upon del small pj, making the changes, here I am using the Hamilton canonical equation of motion, in which del upon h upon del pj, it is qj dot. Qj dot means dqj upon dt. So dt cancels out, it is dqj. That means partial variation of qj. This is equal to dqj. And similarly, from the second expression, del pj, and putting epsilon to be dt and instead of g to be h, I get del pj to be equal to dpj. Now here I have make the transformation from old set of coordinate small pj to small qj plus del qj plus pj plus del pj at a particular time t, and we can see that variation of qj comes out to be exactly the same change in qj. Similarly, the variation in pj comes out to be the exact change in pj. This is obtained by taking our generating function to be equal to Hamiltonian. Hence, we can say that infinitesimal contact transformation are generated by Hamiltonian. That means Hamiltonian is the generator of system motion. So, canonical transformation can be obtained by two methods: bilinear invariant condition or exact differential condition, and the another problem which is of infinitesimal contact transformation. Here the generating function will be changed from f to g, and here the old and new coordinates, they are not exactly the same but they differ only slightly. And by taking our generator as Hamiltonian, we get a motion of system in which the variation in coordinates is exactly the same as variation actually happens. That means del qj will be equal to dqj and del pj will be equal to dpj. Thank you students for watching.